Okay, let's begin. In today's tutorial session, we are supposed to look at a relatively less number of problems than usual. So, first we'll look at adequacy of connectives. Yeah, the first problem is that singleton negation is not adequate. Why is that so? Loudly. It is unary operator, that doesn't mean it cannot show connections between two things. We cannot show disjunctions, how will you prove that? Huh? By induction, how will you use induction? Tell me.
Like for case if you can show that there does not exist a valuation.
I mean, what is a valuation anyway? First, look at what are the formulas. If negation is your only symbol, then what are the formulas that you can construct from a two variable alphabet? We can construct P, we can construct negation P, then double negation P, triple negation P, quadruple negation P, and so on and so forth. Okay. Then similar with Q. Okay, so by induction you can argue that these are all the formulas. And what will be the truth tables if there are only two variables? What is the property of those truth tables that you can extract from this? Exactly half of the values are true, half of the values are false. Well, you make this claim by induction, make this claim and prove by induction that this claim is true. Induction is very easy. What is the induction, what is the base case? For variables, yeah, so I am going to write down the steps, you fill in the details. So, construct all formulas for L equal to PQ with only negation as the connective. Then claim that any truth table, any column of the truth table for a formula contains exactly half T's and half falses. Okay, so this is your claim, and how will you prove this claim? Using induction. What is the base case for induction? P and Q, only the variables. And how many entries are there in a column? 4. Yes, because there are two variables, so 2 to the power 2, 4 things. So base case is P and Q. Yeah, I mean, try that. And inductive cases. What is the inductive case here? How do you generate a more complex formula from an existing one? Just negation. Yeah. So inductive case is if S has the property, I mean the property is the one mentioned here in the claim, then so does negation S, and that's all. You are not supposed to do anything else. As soon as you prove the claim, then you are done. Why? Any connective, any binary connectives which has 3 truths or 3 falses cannot be expressed in this language. So we are done.
Sir, can't we use means cardinality to show this? That
What cardinality?
there is the number of different, the total cardinality of analytic Boolean algebras will be 8 for 2 plus 2 case when L is 2.
Okay, see, we don't want to go there because we haven't defined valuations properly. Unless you define valuation, you cannot define.
Sir, here also we are using the concept of column.
We are using the column for truth table because the truth function is given. Negation's truth function is given. If you remember, we are not trying to do semantics here, we are trying to do more syntax. Yeah, here syntax corresponds to only this. So our normal logical equivalence relies on valuations, and the valuation has a very specific meaning. And what did we prove? Valuation was a function from SL to truth false which satisfies certain conditions, and that function is nothing but a function from L to two valued functions. Now that particular proposition also we haven't shown for only this set of connectives. We have done lot of things, and after that we defined the concept of logical equivalence, and after that we defined the concept of Lindenbaum-Tarski algebra. So we don't want to go as far. Just by counting this won't work. You actually have to go into the nitty-gritties of how formulas are constructed. And then the truth table, whatever truth table we are talking about, that only depends on the truth table for this. Okay, so we only know one connective and we can only use that connective. So we cannot use our usual concept of logical equivalence, unfortunately. Here we are not talking about valuations, like truth tables have to do with truth functions, and truth functions are more syntactic objects. What is a truth function? It is any function from true false to the power n to true false. Now valuation is what we understand, right? That is a semantic concept, but there is no such concept required here. The definition of adequacy of a set of connectives simply states that every truth function, the column for every truth function, we should be able to generate using given set of connectives. So it is a purely syntactic concept. You understand? So therefore we don't need that, we just need this. Yeah, so don't try to use cardinality arguments here. See, I'm not saying that you cannot do it, but you'll have to prove lots of results before you can first approach that. Any questions?
Sir,
Yes?
can't we show the all the equivalence classes generated by this, like P, Q, negation P and negation Q? Only 4 classes are can be generated with negation, and then we can say that for example P disjunction Q cannot be generated from.
But it won't even be a Boolean algebra. When we are talking about Lindenbaum-Tarski algebra, it won't even be a Boolean algebra. What is contradiction and what is tautology? Tell me. In the normal LT algebra, what is the contradiction? What is the formula whose class is contradiction? P conjunction negation P. You don't have conjunction. How will you obtain the zero of the Boolean algebra? We don't have disjunction, P disjunction negation P. We don't have disjunction, so how will you obtain the top element? The algebra there will have a totally different structure. It will be just P negation P, Q negation Q, and they are all on their own. None of them is contained inside any other. It will be an anti-chain of 4 elements. Well, that's really boring. Yeah, and also not the correct way to prove things. The proof the only method that we know of is induction. So if you want to show something is not adequate, then your only method is induction. Yeah, you find out a property. Okay, so then you can complete the proof that any column with 3, any true function whose column consists of 3 truths or 3 falses cannot be written using this, or even 4 for that matter. Yeah, 4 truths, all 4 truths, a tautology or a contradiction, that also cannot be expressed using this. Hopefully you got the idea. What about the second problem, that singleton implication is not adequate? Tautology cannot be constructed? No. P implies P is a tautology. Negation P cannot be constructed. How will you argue?
I can take a single variable.
Single variable, okay, good start. So we start with only single variable case. Then what are the formulas that you can construct? P implies P, then P implies P implies P, or P implies P implies P, and so on and so forth. Then whenever the truth value of P, I mean you consider any column, any row which has value of P listed as true, then what will be the value of the corresponding entry in the column? It will always be true. And how will you prove that? Using induction. So it will always be true, and as a consequence, yeah, what will happen? Negation can never be constructed. Okay, good. So that's your argument, yeah. And here I want you to pay attention. Yeah, that's how mathematics works. Did we really use the full truth table for implication? No. What did we use? Just one row. Whenever P is true, then P implies P is always true. I am not writing a proof of this, by the way. I hope you understand. Now I want you to go a bit further and try to, undo and try to look at problem 4 now. If F0 is an adequate binary connective, it is a singleton adequate binary connective, then we are trying to show that F0 of true is false and F0 of false is true. What is this argument? Tell me.
So if it is true, then it will always be true.
Exactly. Use the same argument that we used for implication. If F0 of true is equal to true, then any formula constructed only using F0 will have the first row will be entirely always true. So you can never express negation. Now that's an observation, because for implication also we did not really use the full strength of the truth table. And because there is some involution acting on truth tables. What is that involution? Involution means a map which is its own inverse, or a map whose square is identity. So the involution is the swapping map, truth and false. Okay, so the same argument will work even for the second part, that F0 of false cannot continue to be false, because then that row is going to create a problem. So F0 of false must be true, F0 of true must be false. Okay, so now let us do some logic. We want to prove 4 by contradiction. Contrapositive. What is the contrapositive of this statement? Tell me.
If else is f naught of t else is false, then this is not it.
If f0 of or, yeah, exactly. That or is important. So under any of, if one of these fails, then you have to show that f0 is not adequate. Right? So don't say that both of them fail together, because this is an and. So conjunction, negation of conjunction is disjunction of negations. So you do that. I will write down a few steps so that you will have some help. So we prove contrapositive. Okay. So suppose f0 of true is not equal to false. Well, not equal to false because we are in a binary world. Not equal to false is being true. Suppose this is true, or false is not equal to true means it is false. So we will show under either hypothesis the truth table, the unary connective negation cannot be expressed using f0 via induction. Okay, and then the argument is simple. You just have to use induction to show this. Yeah, because negation is always supposed to flip. Yeah, here I am going to say use the language L equal to singleton P. Yeah, don't complicate your lives. Make it as simple as possible. Just use this and you are through. With one variable, how do you write a two variable connective when you don't know? Usually when you have conjunction, disjunction, implication, you write them in between two things. But this is f0. How will you write it? f0 of s comma t, right? So just use them as binary functions. Okay. Any questions? Okay, now I think all of you are expert enough to tell me the solution for this. Yes, how do you obtain negation using NOR? P nor P is negation. Okay, I am taking your word, I don't remember right now. And what is conjunction? Wasn't it the same thing with NAND?
So that will be disjunction. So what you said will be disjunction.
Oh, what you said will be disjunction. P nor Q nor P nor Q. That would be disjunction. Okay, good. So if all of you can prove, see, if you want to show something is adequate, then you have to express negation and conjunction or negation and disjunction. Yeah, you don't use induction if you want to prove something is adequate, because what happens is that we already know one adequate set of connectives. What is that? Negation and conjunction. If you can express everything in one adequate set of connectives using your connectives, then you are through. By the way, tell me what is a minimal adequate set of connectives? No, I am not asking you for an example. What is the definition of a minimal adequate set of connectives?
minimum connective that generates all the
Minimum connective, what is the meaning?
number of connectives.
Minimum number of connectives, that's also not true.
Any adequate set that generates all other adequate sets.
That generates all other adequate sets, no. Whenever we talk about minimality, what is the first thing that comes to your mind? No, smallest, but order. It has to do with order. Some kind of order, some kind of partial order. Now what partial order?
Not a subset of any other adequate.
Exactly. It is, no.
Proper.
No. It doesn't have a proper subset which is adequate. Yeah, it is minimal with respect to subset relation, with respect to inclusion. Okay. So, conjunction, disjunction, negation, that is adequate, but it is not minimally adequate. Okay, good. So now that we have established 4, that if f0 is adequate and it is binary, then f0 of true is false and f0 of false is true. Now let us go to the next problem. We need to show that NAND and NOR, you have already shown these two are adequate. Yes, so NAND and NOR are the only singleton adequate sets of connectives. Why?
Because from previously I have shown if it's true or false, it
Uh-huh.
has to be the opposite. So we have only 2 choices left.
Very good. We have only other 2 choices left. So let us write down all such choices. Okay, so this is, let's say, P and Q. And then I'm just going to say F1 of PQ, F2 of PQ, F3 of PQ, and F4 of PQ. These are the only possibilities. We know that true must give you false. So these are all falses, then these are all trues. So the remaining, the 4 possibilities are based on what are the values here. Okay, the first, so this could be true, then this could be false, then this could be true false, or it could be false true. Now, what is F1?
No.
I think F1 is NAND. F1 is NAND, F2 is NOR, F3 is F3 is negation Q, and F4 is negation P. And we have already shown that negations are not good choices. Done. Right? So this is not a hard problem to solve. So these 2 are and these 2 are not. What is the argument here? Consider F3 and F4. Their columns consist of exactly half trues, half falses. Done. Yeah, there is no other thing necessary. Any questions? Okay, let's proceed. So we want to show this result. So this is the semantic deduction theorem. Okay, how will you prove something like that? Contrapositive, very good. By the way, is everybody here familiar with the difference between contrapositive and contradiction? If you want to show A implies B, then what is contrapositive? Okay, I know all of you know that. Yeah, that much is. So you only start with the assumption that B fails and you conclude that A fails. Okay. Whereas, what is the proof by contradiction?
Assume that B fails.
We assume that?
We assume A and assume that B fails.
Exactly. We assume that A holds and B fails. Yeah, if these 2 contradictory things are assumed, then we conclude a contradiction. right? So B fails is common to both of those assumptions, but assume that A holds and B fails. So tell me one proof that we have done using real contradiction. Cantor's theorem. Yes, in Cantor's theorem we assume that the bijection holds, and then later we also assume, what do we assume? Do we assume, what is the conclusion?
Conclusion is that the pre-image of the constructed set does not exist.
Right, so I think the Cantor's theorem is a bit more complicated logically to think about.
So when we prove that maximal is equivalent to prime is equivalent to...
Exactly. That proof is a very good example. Yeah, we assumed that, I mean, one of those two conditions, yeah, out of those three, maximal, prime and ultra. Yeah, whenever we want to prove, let's say the exam question, yeah, what was that? Ultra implies prime. So we assume that prime fails and ultra holds, and then we obtain a contradiction. Okay, so that's a proof by contradiction. And whenever we use proof by contradiction, we are actually using a law of logic. It is a meta law of logic. Yeah, and that law is called law of the excluded middle. Law of excluded middle. Now excluded middle means the world is binary. Okay, it simply says that any statement, let's say phi, so phi or negation phi is a tautology. Okay, law of excluded middle says that phi or negation phi is tautology. So basically one of these two must always hold. Phi or negation phi, one of these two must hold. So whenever we show that negation phi doesn't hold, then by the law of excluded middle we conclude that phi must hold. Now some mathematicians, there is a community of them, they are called as constructivists or intuitionists. Yeah, and in particular intuitionists, they do not like this law because it doesn't provide you with any constructive justification of why phi should be true. What we usually end up proving is that negation phi doesn't hold. But it's not really a valid reason for concluding that phi must hold. Yeah, so intuitionists or constructivists, they both always reject this law, and then they have a separate logic, separate meta level logic. Whatever we are doing is called classical propositional logic. But intuitionists, they use intuitionistic logic, where they basically reject this law. Okay, phi or negation phi is tautology or is truth. They reject this law. And whenever you reject this law, then most of the things that you can do, especially in constructivism, they can always be taught to a computer. Computer also doesn't really understand phi or negation phi equal to true. Yeah? Because that's not a valid thing. It doesn't provide an example. It doesn't provide justification for why phi must be true. In constructive logic, you cannot use proof by contradiction. You understand? So I also want to bring to your attention the fourth law that we wrote yesterday. The fourth law, logical axiom. What was that? Law of contraposition. Right? So that also will not hold there. Okay, so phi or negation phi for intuitionistic logic, it goes very close to truth, but it doesn't exactly go there. Okay, so there is a branch of logic called intuitionistic logic, especially there is a branch of philosophy which uses only the things for which we have evidence. It's more like science, right? If we want to believe in something, then we need evidence for that. So that branch is called intuitionistic logic. It's also a branch of mathematical logic and philosophical logic. Okay, let's come back here. Now what proof we are going to use here? So whenever you write in future, yeah, I am sure that even very senior people also make these mistakes. Whenever you write a proof by using contrapositive or contradiction, I want you to pay attention. The main lessons of this logic and set theory course are these ones, and not the theorems that we are studying. Okay? I want you to pay close attention to whether you are actually using contradiction or only contrapositive. Yeah, please pay attention. Okay, let's do this. Well, let us prove only one side, the second one we can leave as exercise. Yeah, which one should we prove? Huh? Okay, so suppose, so I am proving this side, yeah, contrapositive. I am just writing keywords, please don't do that. Suppose S doesn't model T implies U, then what will happen? Then there is a valuation. See, I am not writing there exists here. I am just saying in words that there exists a valuation. We are doing logic, so in logic you should never use meta level quantifiers. You should always write them in English. So then there exists a valuation V such that V of S is true. What is the meaning of V of capital S being true? For all formulas in capital S, V of that is true. And V of T implies U is true. Okay. Then what is the meaning? Sorry, false. What is the meaning of V of T implies U being false? Yes, i.e. V of T is true and V of U is false, because that's the only place true implies false cannot happen. So that's the only place where it happens. So now what happened? So there is a valuation V which makes capital S true and T true but U false. So therefore we have witnessed and I lied when I said let's do only one side. This is if and only if. Done? So this part is really easy. Okay, let's go to the next one. Same thing here. Can you do this please? Yeah, there is nothing hard over here. In fact, here you don't even have to use contrapositive, right? You just do it directly. Yeah, whenever this is true, then that is true. So whenever this is true, then this is also true. That is if and only if. So V of capital S union TT prime, let me write that. V of S union TT prime is true if and only if, T and T prime are both true, What is the test for that? That T conjunction T prime is true. So V of S union T conjunction T prime is true. And then the rest is easy. So this is for any V. Right, so whenever the left hand side is true here, then U is true. If you assume that, then whenever the left hand side of the right hand side is true, then U is true, and vice versa. Okay, so nothing to do here. Let's do monotonicity. What is semantic monotonicity? Yeah, the set of logical consequences of capital S is contained inside the set of logical consequences of S prime. Whenever S is contained inside S prime. Yeah, that's our argument. Okay, so now how will we show this? Any ideas? Contrapositive? Why? Take a valuation, yeah? So assume assume T is a logical consequence of S and V is a valuation such that V of S prime is true. Yeah, what is our claim?
V of P is true.
V of little t is true. And how do we prove this?
Just by definition.
V of capital S prime is true and S is contained. So therefore
V of S is true.
V of S is true, and because S models T, therefore V of T is true. Done. Yeah, since S is subset of S prime and V of capital S prime is true, V of capital S is true. Now further, since T is a logical consequence of S, we get V of little t is true. Done. So there is nothing to be done here. It's very simple. Syntactic monotonicity is also simple. Tell me what's the idea here?
And assume the proof is n lines and
Correct. Assume the proof is n lines.
the first line will have to be LA or NLA. And
First line is LA or NLA, or any line which is LA or NLA,
yeah, you can replace it directly.
you can replace it directly. Yeah. So start with a proof of T is deducible from S. Now we use induction on line number or line reasoning. Well, let me say line reasoning. So there are 3 steps in induction. There are 2 base cases and 1 inductive case. So base case 1, what's that? LA. So if T is, if Ti, yeah, so suppose, suppose ith line, let me write it properly. Suppose ith line is the sequent S proves Ti, LA. Then what do you conclude about Ti? Ti is a tautology. So the truth of tautology doesn't really, it follows from anything. Yeah, so we can directly replace. So replace it with S prime proves Ti La. Nobody can stop us from doing this. Yeah, because La follows from anything. What about base case 2? Suppose ith line is the sequent S proves Ti and La. Then what will happen?
TI belongs to
Then Ti belongs to
S.
yes, then Ti belongs to S, which is a subset of S prime. So therefore S prime is the replacement. Okay, what is inductive case? Not empty, MP. Yeah, MP, right. MP. So modus ponens on two previous lines. So the two previous lines have been replaced by, I mean their LHS has been replaced by S prime. Yeah, so well, write it. Yeah, their LHSs have been replaced by S prime, and therefore, I mean, what should they be? The line Ti, suppose ith line is the sequent S proves Ti MP on two previous lines. So let me write them JK. So then, without loss of generality, jth line is S proves Tj, and kth line is, what should it be, kth line? S proves, not T, I mean don't say Tk, yeah, it has to be of a specific form. Tj implies Ti, very good. So by induction hypothesis, yeah, by induction hypothesis we have replaced the LHS of jth and kth lines by S prime, and therefore by MP, now new reasoning, therefore by MP, therefore MPJK gives required new sequent. Right, so we had replaced jth and kth lines by S prime S prime. So therefore in the new one also S prime proves Ti. S prime proves Ti. Yeah, that's the new sequent, and still the proof is not yet complete. When do you say it's complete? Since the last sequent is S proves T, in the original proof the last sequent is S proves T, therefore in the new proof we have also replaced it by S prime proves T. Yes, so I will write it here. Since the last sequent is in the original proof is S proves T, we have replaced it by S prime proves T, and by induction we are done. So we have obtained a proof of T from S prime, a formal proof of T from S prime. Understood this? Yes.
So here are we saying that the Tj and Tj implies Ti are LA or NLA?
They are?
LA or NLA?
No, we are not saying that. They could themselves be obtained from MPs. But by induction hypothesis, that's why I actually write line numbering. Okay, so it is induction on line numbering. So every line up till this point has been done. When you apply the first MP, what should be the minimum line number for MP? 3. Yes. So that means first two were either LA or NLAs. So by induction on line number, we can go there. Yeah, so by induction we have already converted the previous applications of MP to a larger left hand side. Okay, any questions about this? Anybody willing to take up this challenge? Yes, one, and you have it, show it to me. Yes, write it. Good. You just have to be creative. Yeah. I have been told by psychologists, yeah, some friends, that here the human mind is literally binary. There are very few people who can immediately see formal proofs, and there are others who even after a lot of practice cannot see them. So in exams I never ask unseen formal proofs. Yeah, because it's very hard, like you can spend hours trying to do them and not see. When I looked at his solution, I only looked at the line number. Because he obtained the proof on, completed the proof in 5 lines, it has to be correct. I knew that I know a solution which is 5 lines. You have to be very creative over here with too many S's. Make sure you parenthesize them appropriately. Now just apply 2 MPs. I do not know any shorter proof. In fact, I taught this course at the logic school, like propositional logic and predicate logic, ISLA 2020. I taught this. It's called Indian School on Logic and Applications, and during that period there were a couple of enthusiastic students who actually coded up Hilbert style propositional calculus. And yeah, I mean this is a decidable logic, so you can code it up and write down all the statements whose proofs can be given in a fixed number of lines in a given set of variables. Thank you. Yeah, here the idea is that there is no idea. Yeah, you just have to try. Trial and error is the only method here. It either works or it doesn't. I'll give you some time to think about it. Yeah, 2 applications of LA1 and 2 applications of LA, 1 application of LA2, and then you are through. Okay, our time is up, but there is one more question remaining, and let us do that quickly. After that, I will show you this screen again. Okay. What is the DNF corresponding to P disjunction Q? What is the CNF corresponding to P disjunction Q? Nothing changes. For B, it is negation P or negation Q or R. Yeah, this is both CNF and DNF. You don't have to go any far. Okay, then what about this P conjunction Q if and only if R? P conjunction? Loudly, Arnav.
P conjunction negation Q disjunction R.
P conjunction?
Negation Q disjunction R. Again conjunction with Q disjunction negation R.
Okay, what is this? CNF. What is DNF? Just a moment. Somebody here.
P conjunction Q conjunction R.
P conjunction Q conjunction R.
Disjunction P conjunction negation Q. Disjunction.
P conjunction negation Q.
Conjunction negation R.
Conjunction negation R. Okay. How did you obtain this last one?
By calculating the
Atoms. Calculating the atoms below it. So that is the simplest method. And how did you obtain the top one? Just by the simplification. Yeah, so De Morgan's laws are here, are there to help. Then distributivity is also there to help. Yeah, there could be complicated expressions, but you can always go through them properly and do this.